Hello class, this is Ms. Riggins with today's video on sections 6.1 and 6.2 on antiderivatives. As you're watching the video, please remember to write down important notes, equations, statements, or formulas. Feel free to pause, rewind, or replay the video as often as you need. And at the conclusion of watching the video, write down a brief summary about what occurred in the video and submit that summary as well as a top question via the online whisk the day before class. All right, let's begin. You have heard us talk about antiderivatives, and this video is really going to be more about what antiderivatives are and how we can use them to solve problems. So let's begin. If you recall, we had two different functions, a little f function and a big F function. And the relationship between the two is that one was the derivative of the other. So this statement is important to know. If the derivative of big F is little f, then we call big F an antiderivative of little f. So for an example, the derivative of x squared is 2x. So then that would mean that x squared is an antiderivative of 2x. Because when I take the derivative of x squared, I get 2x. But if you notice, I said is an antiderivative, which means it's not the only one. X squared plus 3 is also an antiderivative of 2x because when I take the derivative of x squared plus 3, I get 2x. So it's still x squared plus 3 is an antiderivative of 2x, as well as x squared minus 23, as well as x squared minus 1.5, and so forth and so forth. In other words, x squared plus any constant number is going to be an antiderivative of 2x. And that's why we say the family of antiderivatives of 2x is of the form x squared plus c. So there's a difference between an antiderivative and the family of antiderivatives. This can be any expression, x squared plus any number, but the family of antiderivatives is a group of functions whose derivative is going to be, in this case, 2x. Now, how can we use the derivative of a function to graph the original function? Well, we can be a little bit more specific using the relationship between antiderivative and its function, a function and its antiderivative. So let's take a look at this graph, which is the graph of a derivative of a function. And we're going to determine what an antiderivative is of this function by using what we know about derivatives. So in this case, from x equals 0 to 2, the graph of the derivative function is a horizontal line, which indicates that the slope of the tangent line of the original function is the exact same value, which seems to be very much like a linear function. And as we can see here, from x equals 2 on, the graph of the derivative function is a linear line with negative slope, which means one of two things. Since the line is linear, it means that the original function must have changing slopes of tangent lines, but they change at a constant rate, which would imply a quadratic function. And as we can see here, from 2 to 4, the derivative is positive, but from 4 on, the derivative is negative, which implies that the parabola is opening down, which means we would have a graph that looks something like this. A straight line. Oops, I cannot draw a straight line. And then a parabola. Gosh, I cannot draw a straight line. Well, let me not even try that. So I do have a picture of someone who drew a straight line and then the parabola. But as you can see, we have more than one answer because even though we know what the shape of the curve is, we have more than one answer because you can have different positions of the exact same shape as we see here. In this position, f of 0 is 0, and in this position, f of 0 is 1, and we can draw countless more. So every antiderivative is going to look like this, but the position on the axes is going to be dependent on what its constant is. Okay? So how do we represent that? Well, let's start with the problem. Let's say I have one of the values of the original function, and I have the derivative of the function. So now I have a derivative function graph, and I have one function value of the original function. And I want to sketch or get an idea about what the original function looks like. Well, from the derivative graph, I know that the zeros of the derivative graph are the critical points of the original function. So I know that I have critical points at x equals 0, x equals 20, and x equals 30. I also know that the local maximum and minimum of the derivative graphs are also the inflection points of the original graph. So that means that my original graph has inflection points at x equals 10 and x equals around 25. Okay, so now I can use what I know about definite integrals to come up with some function values for these important points. So I have these points being let's say the critical points and the inflection points 0, 10, 20, 25, and 30. Well, we know that we can use the area between the function and the x-axis to get an answer for the idea of the definite integral. So let's start from x equals 0 to x equals 0. Well, we don't know what that area is, so we can't say anything, but we do know something else, but we'll talk about that later. So let's take a look at it from x equals 0 to x equals 10. I got 100. Now, some of you say, how did you get 100? Well, I got 100 because I actually looked at the area underneath the curve in the x-axis, and I got a triangle with these units, 10 and 20, and got that value. Then from 0 to 20, this is a triangle that results. So this is the accompanying area. And then we get from 0 to 25. Well, this is a triangle that results. And if I add up the areas, I get now 225. And then from 0 to 30, I add up this and I get 250. But as you know, even though we're finding the area under the curve, another way to represent this information, we can use this information in terms of the definite integral. If you recall this statement right here. And so if I let my a be equal to 0, then I already know what big F of 0 is. That's 100. And so really the area under the curve from x equals 0 to 10 should be equal to whatever big F B is minus 100. Well, we know that the area from 0 to 10 is 100. So if this value is 100 and something minus this is equal to 100, then F of B must equal to 200. So let's add another row to our chart so we can get an idea. And we know that from 0 to 0, it's going to be 100. But when B is 10, then that means that our real area should be 200. So that 200 minus 100 would give me my area of 100. Okay, I hope I said that right? Yes. So this would also equal 100 if F of B is 200 and F of A is 100, and vice versa. And so same thing here, we would end up with this being equal to 300, because 300 minus 100 would give me 200. And then here we have a little difference, because now our area under the curve, under the graph, is on the negative side. So we're actually going to do this a little bit differently, because in order to be able to get 225 from 100, you would say, oh, this has to be 325, because 325 minus 100 is 225. But remember that since it's underneath the curve, we would subtract this area. So our actual answer here would be 275. And then when B is equal to 30, that would be 350. Did I say that right? No, sorry. It's 250, okay, because we are subtracting an extra 25 from the previous area. So we end up with something that looks like this, which is important because this gives us our values for our critical points. So 0, 100 we know is a point on our graph. 10, 200 is a point on our graph. 20, 300 is a point on our graph, and vice versa. So now we have information to be able to complete our graph, and our graph would look something like this. As you can see here, we have our critical points, we have our inflection points as well, and now we have actual function values. So we have a better way of graphing the graph. All right, so I know that was like a lot of confusion, but here's a more general. So take a look at this, and as I was telling you earlier, we from x equals 20 to 30, the graph is below the x-axis, so now we're subtracting the area from the total area, and that's why we get 275, 275, and 250 respectively. All right, let's move on to the next section, which will be a lot quicker. Constructing antiderivatives analytically, okay? And we've already been doing that already, so this is just going to be a way to summarize what we've done as well as add on some other tools that we've already used. So first of all, if big F prime of x is equal to 0 on an interval, that means the original function big F of x is equal to some constant on this interval. So in other words, if we ever have a derivative of a function being equal to 0 for all x, then we know the original function would have to be the constant. I know you guys are like, that's obvious. That's true. And if f and g are both antiderivatives of f on an interval, then they are the same function. They're part of the same family of functions. They just differ by a constant. And we can prove that. Take the derivative of both sides, and we get derivative of gx is equal to the derivative of f of x. So that's basically what this means here. But we're going to use a new term called the indefinite integral. And the difference between the indefinite integral notation and the definite integral notation is, as you can see, the indefinite integral notation does not have the points of integration on the end. And that's because the definite integral represents a number value. I will compute a number, whereas the indefinite integral doesn't represent a number. It represents a family of functions that has this as its antiderivative. Okay? And so in this case, to determine this, all we would have to do is equal a family of functions, big F, such that the derivative of f, big F is equal to little f. And so this is what this answer looks like for an indefinite integral. So the indefinite integral will never give you a numeric value unless you have a constant function. But anyway, so let's take a look at some properties very quickly. Popular properties, you guys already know them. I'm going through them so you can see. We already know the first two. I'm going to come back to this one. We already know that the derivative of an exponential function is itself. And so this is obvious. And we already know that the derivative of cosine and sine are each related to each other. So you should know and memorize these. This one right here, the reason why we say this has to be an absolute value is because if I say 1 over negative 3x, well, natural log functions cannot take negative values. So natural log for a negative input value is not defined. So we have to make sure the inputs are always positive. In order to do that, that would mean that this original derivative function would have to be positive as well, or the absolute value. Okay? And then the last thing that you should know, it's kind of obvious that we can break up indefinite integrals, just like we could break up definite integrals, and we can multiply a scalar times an indefinite integral as well and get the same type of answer. And just to summarize how you would determine what the indefinite integral is you must first find big F, and you can find big F using the previous tools. And if you want to use the definite integral, then calculate f of b minus f of a. And that's it. Sorry it took so long, but I wanted to do some examples.